Probability. Counting. You already know how to count, or you wouldn't be taking a college-level math class, right? Well, yes. But what we'll really be investigating here are ways of counting efficiently. When we get to the probability situations a bit later in this chapter, we will need to count some very large numbers, like the number of possible winning lottery tickets. One way to do this would be to write down every possible set of numbers that might show up on a lottery ticket. But believe me, you don't want to do this. Basic counting. We will start, however, with some more reasonable sorts of counting problems in order to develop the ideas that we will soon need. Example 21. Suppose at a particular restaurant you have 3 choices for an appetizer: soup, salad, or breadsticks, and 5 choices for a main course: hamburger, sandwich, quiche, fajita, or pizza. If you are allowed to choose exactly one item from each category for your meal, how many different meal options do you have? Solution 1. One way to solve this problem would be to systematically list each possible meal. Assuming that we did this systematically and that we neither missed any possibilities nor listed any possibility more than once, the answer would be 15. Thus, you could go to the restaurant 15 nights in a row and have a different meal each night. Solution 2. Another way to solve this problem would be to list all the possibilities in a table. In each of the cells in the table, we could list the corresponding meal. But if we didn't really care what the possible meals are, only how many possible meals there are, we could just count the number of cells and arrive at an answer of 15. Which matches our answers from the first solution. It's always good when you solve a problem 2 different ways and get the same answer. Solution 3. We already have 2 perfectly good solutions. Why do we need a third? The first method was not very systematic, and we might easily have made an omission. The second method was better, but suppose that in addition to the appetizer and the main course, we further complicated the problem by adding desserts to the menu. We've used the rows of the table for the appetizers and the columns for the main courses. Where will the desserts go? We would need a third dimension, and since drawing 3D tables on a 2D page or computer screen isn't terribly easy, we need a better way in case we have 3 categories to choose from instead of just 2. So back to the problem in the example. What else can we do? Let's draw a tree diagram. This is called a tree diagram because at each stage we branch out, like the branches on a tree. In this case, we first drew 5 branches, 1 for each main course, and then for each of those branches we drew 3 more branches, 1 for each appetizer. We count the number of branches at the final level and get 15. If we wanted, we could instead draw 3 branches at the first stage for the 3 appetizers and then 5 branches, 1 for each main course, branching out to each of those branches. Okay, so now we know how to count possibilities using tables and tree diagrams. These methods will continue to be useful in certain cases, but imagine a game where you have 2 decks of cards with 52 cards in each deck, and you select 1 card from each deck. Would you really want to draw a table or tree diagram to determine the number of outcomes of this game? Let's go back to the previous example that involved selecting a meal from 3 appetizers and 5 main courses and look at the second solution that used a table. Notice that one way to count the number of possible meals is simply to number each of the appropriate cells in the table, as we have done above. But another way to count the number of cells in the table would be multiply the number of rows by the number of columns to get 15. Notice that we could have arrived at the same result without making a table at all by simply multiplying the number of choices for the appetizer by the number of choices for the course. We generalize this technique as the basic counting rule. Basic counting rule. If we are asked to choose one item from each of two separate categories where there are M items in the first category and N items in the second category, then the total number of available choices is M multiplied by N. This is sometimes called the multiplication rule for probabilities. Example 22. There are 21 novels and 18 volumes of poetry on a reading list for a college English course. How many different ways can a student select one novel and one volume of poetry to read during the quarter? There are 21 choices from the first category and 18 for the second, so there are 21 multiplied by 18 equals 378 possibilities. The basic counting rule can be extended when there are more than two categories by applying it repeatedly. Permutations. In this section, we will develop an even faster way to solve some of the problems we have already learned to solve by other means. Let's start with a couple examples. Example 25. How many different ways can the letters of the word math be rearranged to form a four-letter code word? This problem is a bit different. Instead of choosing one item from each of the several different categories, we are repeatedly choosing items from the same category. The category is the letters of the word math, and each time we choose an item, we do not replace it. So there is one fewer choice at the next stage. We have 4 choices for the first letter. Say we choose A, then 3 choices for the second, M, T, and H. Say we choose H, then 2 choices for the next letter, M and T. Say we choose M, and only 1 choice at the last stage, T. Thus, there are 4 multiplied by 3 multiplied by 2 multiplied by 1 equals 24 ways to spell a code word with the letters in math. In this example, we needed to calculate n multiplied by n minus 1, multiplied by n minus 2, and so on, 3 multiplied by 2, multiplied by 1. This calculation shows up often in mathematics and is called the factorial, and is noted n factorial. Factorial. N factorial equals n multiplied by n minus 1, multiplied by n minus 2, and so on, 3 multiplied by 2 multiplied by 1. Example 26. How many ways can 5 different door prizes be distributed among 5 people? There are 5 choices of prize for the first person, 4 choices for the second, and so on. The number of ways the prizes can be distributed will be 5 factorial equals 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1 equals 120 ways. Now we will consider some slightly different examples. Example 27. A charity benefit is attended by 25 people and 3 gift certificates are given away as door prizes. One gift certificate is in the amount of $100. The second is worth $25, and the third is worth $10. Assuming that no person receives more than one prize, how many different ways can the 3 gift certificates be awarded? Using the basic counting rule, there are 25 choices for the person who receives the $100 certificate, 24 remaining choices for the $25 certificate, and 23 choices for the $10 certificate. So there are 25 multiplied by 24 multiplied by 23 equals 13,800 ways in which the prizes can be awarded. Example 28. 8 sprinters have made it to the Olympic finals in the 100-meter race. In how many different ways can the gold, silver, and bronze medals be awarded? Using the basic counting rule, there are 8 choices for gold medal winner, 7 remaining choices for the silver, and 6 for the bronze. So there are 8 multiplied by 7 multiplied by 6 equals 336 ways the 3 medals can be awarded to the 8 runners. Note that in these preceding examples, the gift certificates and the Olympic medals were awarded without replacement. That is, once we have chosen a winner of the first door prize or gold medal, they are not eligible for other prizes. Thus, at each succeeding stage of the solution, there is one fewer choice. 25, then 24, then 23 in the first example, 8, then 7, then 6 in the second. Contrast this with the situation of a multiple choice test, where there might be 5 possible answers, A, B, C, D, or E, for each question on the test. Note also that the order of selection was important in each example. For the 3 door prizes being chosen first means that you receive substantially more money. In the Olympics example, coming in first means that you get the gold medal instead of the silver or bronze. In each case, if we had chosen the same 3 people in a different order, there might have been a different person who received the $100 prize, or a different gold medalist. Contrast this with the situation where we might draw 3 names out of a hat to receive a $10 gift certificate. In this case, the order of selection is not important since each of the 3 people received the same prize. Situations where the order is not important will be discussed in the next section. We can generalize the situation in the 2 examples above to any problem without replacement where the order of selection is important. If we are arranging in order our items out of n possibilities, instead of 3 out of 25 or 3 out of 8 as in the previous examples, the number of possible arrangements will be given by n multiplied by n minus 1 multiplied by n minus 2 and so on, n minus r plus 1. If you don't see why n minus r plus 1 is the right number to use for the last factor, just think back to the first example in this section where we calculated 25 multiplied by 24 multiplied by 23 to get 13,800. In this case, n equals 25 and r equals 3, so n minus r plus 1 equals 25 minus 3 plus 1 equals 23, which is exactly the right number for the final factor. Now, why would we want to use this complicated formula when it's actually easier to use the basic counting rule as we did in the first 2 examples? Well, we won't actually use this formula all that often. We only developed it so that we could attach a special notation and a special definition to this situation where we are choosing our items out of n possibilities without replacement and where the order selection is important. Permutations. N permutations of size r equals n multiplied by n minus 1 multiplied by n minus 2 and so on, n minus r plus 1. We say there are n permutations of size r that may be selected from among n choices without replacement when order matters. It turns out that we can express this result more simply using factorials. N permutations of size r equals n factorial divided by n minus r factorial. In practicality, we usually use technology rather than factorials or repeated multiplication to compute permutations. Combinations. In the previous section, we considered the situation where we choose our items out of n possibilities without replacement and where the order of selection was important. We now consider a similar situation in which the order of selection is not important. Combinations. We say that there are n choose r combinations of size r that may be selected from among n choices without replacement where order doesn't matter. We can also write the combinations formula in terms of factorials. N choose r equals n factorial divided by open parentheses n minus r open parentheses factorial r factorial. Expected value. Expected value is perhaps the most useful probability concept we will discuss. It has many applications from insurance policies to making final decisions, and it's one thing that the casinos and government agencies that run gambling operations and lotteries hope most people never learn about. Expected value is the average gain or loss of an event if the procedure is repeated many times. We can compute the expected value by multiplying each outcome by the probability of that outcome, then adding up the products. So in general, If the expected value of a game is negative, it is not a good idea to play the game, since on average you will lose money. It would be better to play a game with a positive expected value. Good luck trying to find one. Although, keep in mind that even if the average winnings are positive, it could be the case that most people lose money and one very fortunate individual wins a great deal of money. If the expected value of a game is 0, we call it a fair game, since neither side has an advantage.